Welcome back to Chem 4300. In this video, we're going to continue Chapter 9 on electrodynamics, and now we're going to use Maxwell's equations to get an understanding of the nature of light. So here they are in their full glory. These are Maxwell's equations, and we see now that the divergence and curl of vector field quantities are not anything to get too frightened by, and they all make sense. And we see that these are the constraints that relate the electric field, the magnetic field, the current field, and the charge field. All those scalar and vector field quantities have to be related by Maxwell's equations. Let's look at a simple case where we remove all of the charge and the currents that are present. So in other words, let's go into empty space where there's no current and no charge present, and these equations simplify down to these equations here. And what we have are first order differential equations involving electric field vectors and magnetic field vectors. And they're coupled. So whatever the rate of change of B is, it involves electric field here and vice versa over here. So we'd like to find a way to decouple these differential equations so that we have a differential equation only for the electric field and a differential equation only for the magnetic field. So this is something that Maxwell did and as he was working on his equations, and this is something that we can do here very simply. So let's see how that derivation works. So let's take these equations here, and let's take this one, which is Faraday's law, and let's take the curl of both sides of that term. So if I take the curl of the left side, I end up with the curl of a curl. And then on the right side, I have just the curl of this differential of B with respect to time. But this term here, the curl of a curl, that there's a vector calculus identity that you can look up that tells you that that is equal to the gradient of the divergence of the electric field minus the Laplacian operator applied to the electric field. Now, this term right here, these two terms right here, if we look at them carefully, you see that the divergence of the electric field is something that we know from the A term, Gauss's law, is going to be 0 in this case because there's no charges around. So that term will go away, and we'll be left with just this side, which I'm going to rewrite down here. And now what I'm going to do is I'm going to do a little trick here, and I'm going to slide that curl operator past the differential and rewrite it like this, and this is valid, you can check this, that I now get the negative partial with respect to time of the curl of B. This part right here I recognize as up here as just equal to the displacement term that Maxwell proposed, the derivative of E, and now I see the way out. I see how I can get rid of the magnetic field part, I can substitute that into there, and I end up with a decoupled second order differential equation for the electric field vector. Okay, now this is for a vector quantity, not a scalar quantity, but nonetheless, it just involves the electric field. Now, if you look at this, you might recognize that that equation looks exactly like the classical wave equation, except here it's working with a vector quantity, but nonetheless, it's still a wave equation, so we know the solutions to this differential equation can be waves. And that, of course, was something that Maxwell realized too when he was looking at that. So this equation, this decoupled equation for the electric field is a vector wave equation. Similarly, we could do the calculation for the B field, and we get a decoupled second order partial differential equation for the B field that is a wave equation also. So we have two wave equations, and they both have the same coefficient in front. And of course, you know that for a wave equation, that's just 1 over the velocity of the wave, the Vp squared. So if I look at the form of these wave equations, I recognize that these describe waves that are moving in space with the velocity of 1 over the square root of the magnetic constant times the electric constant. So if you take Maxwell's equations, you decouple them, you get wave equations for the E field and the B field with wave velocities, that's 1 over the square root of these two fundamental constants that come from electrostatics and magnetostatics. Now, Maxwell saw this, And of course, when you evaluate this, you get the speed of light. So these waves that are associated with these wave equations are going to be moving at the speed of light. Now, this was a bit of a surprise, and you can't help but make that association, and certainly Maxwell did in 1862. He said, "We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena." So there you have it. That was the first time, when 1862, when you decouple the electric and magnetic field differential equations, Maxwell's equations, to get decoupled equations for E and B, that you see that you have a wave that can exist that's moving at the speed of light. So maybe light is a wave that is electromagnetic in origin. Now remember that there are constraints between the E fields and the B fields, right? And so we know that whatever wave we produce, that the electric field and the magnetic fields of this light wave have to follow the constraints of Maxwell's equations, right? So let's see how that works out then for these E fields and B fields that are traveling through space as waves. So first of all, we know that we're going to have the same frequency and wave number for Ex, Ey, Ez, Bx, By, and Bz if we're going to satisfy those equations. So what we're going to do is we're going to start with a solution, just like we've done before. We're going to take, for 3D, we're going to take 3D plane wave harmonic solutions. So let's just take these as our potential solutions. We're going to use complex notation, but we can still know that in the end we'll take the real part to get the physical part of the solution. But we're going to write it in complex form. And of course, you recognize that the k vector here, the wave vector, dot r, is just going to define a plane of constant phase, and the direction of the wave is perpendicular to that plane. So that direction of propagation is the wave vector. And if we plug these guys into those differential equations on the previous slide, you find right away the dispersion relationship. And the dispersion relationship tells you that the frequency is equal to the speed of light times the magnitude of the wave vector. All right? Next thing that you learn is that Maxwell's equations tell you that the E field and the B field have to be perpendicular to the direction of propagation. And you get that from just substituting them into the Gauss's law for electricity, for E fields and B fields. By this constraint here shows you that the E and B field have to be perpendicular to the direction in which the wave is propagating. Similarly, Maxwell's equations also tell you that the E field and the B field have to be perpendicular to each other. And you get that by going over here to Faraday's law, which, plugging in the wave equations, you'll find that K cross E has to be equal to omega times B. So this cross product, K cross E, tells us that B is perpendicular to K and E. So now we learn that K and E and B are all perpendicular to each other. And so we get that constraint from Maxwell's equations. Also, the cross product tells us that for this solution, that there's a relationship. It tells us that the magnitude of K and E is equal to, here we see, omega B. So we see that the size of E is related to the size of B and vice versa. And that proportionality is the speed of light. Now this is for the plane wave solution that we find this particular constraint. So taking it all together, then we find that the E field and the B field are perpendicular to the direction of propagation, and that the E field has to be perpendicular to B also with this kind of relationship. And so we can now draw our sinusoidal wave, our harmonic solutions, and we can draw the picture that I'm sure you've seen dozens and dozens of times before, but now we see that it comes out of the constraints of Maxwell's equations. And we see that we have a oscillating electric field perpendicular to, we have an oscillating magnetic field, and the wave is moving in a direction, a propagation direction that's perpendicular to E and B. And so for our harmonic plane waves, we can write down the real parts, and we have these solutions here. Okay. So that's it. That's our derivation of the electromagnetic waves that we associate with light that comes out of Maxwell's equations. And so shortly after that, well, a few years after that, people realized that, okay, now we understand the nature of light is electromagnetic. Is there ways that we can generate light other than, say, lighting a candle or designing a light bulb? And this is when people like Heinrich Hertz realized that they could find ways to generate electromagnetic waves and detect them. So Heinrich Hertz was the one who first generated radio waves and was able to detect them. And you can imagine, sort of the technological applications for that, right? And so, and that, of course, earned him a place on a German postage stamp. And so here's some classifications of light in terms of the electromagnetic spectrum, right? And so what Heinrich Hertz was able to generate were radio waves, which are down here in the kilohertz, the megahertz range here. Beyond that, as the wavelength gets smaller and smaller, or the frequency gets larger, we move into microwaves. And then eventually, we go into terahertz range, and eventually we reach the visible light range, which our eyes are sensitive to. The electromagnetic waves in the visible range is what our eyes can detect. And then you keep going past that to ultraviolet, and then into soft X-rays, and then eventually at wavelengths down in the order of picometers, you're into X-rays and gamma rays. And of course, these are what are called ionizing radiations, and we actually don't have at this point a way of understanding that, because you'll need to learn that light can actually be thought of as a photon when we get to the quantum theory of light. But at the moment now, where we're looking at the classical wave picture for light, and as we know for classical waves, the energy in the light is related to the amplitude, so it shouldn't be related to the wavelength. So the fact that these ionizing radiation is light that can actually start ripping electrons off the atoms and out of molecules doesn't quite make sense that these will do it, but the other guys won't, because the same small amplitude of radio waves should be able to do the same thing as the same small amplitude of ionizing radiation. But in fact, actually, we'll learn when we get to black body radiation and learn about quantization of light that the energy of light waves is carried in the wavelength. This depends upon the wavelength. So we'll leave it at that, and the next thing we'll talk about is further aspects of light, such as polarization and then the energy that's transferred.